I need you.
Excellent.
All right. Hi, everybody. Welcome to GAAC. Our speaker is Vedant Chandra, who is a doctoral candidate at the Harvard Smithsonian Center for Astrophysics. His research interests include large data sets, custom spectroscopic surveys, and the history of the Milky Way, among many other topics. Chandra works as part of the Sloan Digital Sky Survey and H3 survey collaborations, and the Max Planck Institute for Astronomy, where he's investigating the formation and development of the Milky Way. And here he's going to be talking about the biography of the Milky Way. So please welcome Vedant Chandra.
Thank you. Thank you so much for that really kind introduction. It's really wonderful to be here. Wish I could have come up in person, but hopefully someday I'll be able to come up. So yeah, to start with, I'll just tell you a little bit about myself, about how I got here. I grew up in New Delhi, India. So I did my high school up to there. What you see here is this monument called the Qutub Minar. It's, I think, 500 years old. That was a mile away from where I grew up. So my city was, filled with a lot of history. And if you ever have the opportunity, you should definitely visit it. After high school, I found myself at Johns Hopkins in Baltimore, Maryland, where I studied physics for my undergraduate degree. That's where I really learned that astronomy could be not only a hobby, but also a career. And that's really what got me into astronomical research and brought me to where I am today, which is as a PhD student at Harvard at the Center for Astrophysics. And I really would encourage anyone who hasn't already done so to come down and visit us. Every semester, at the start of the semester, we announce public observatory nights where we have a student or a member of the faculty lead a talk and eventually take you up. And, I think our telescopes are definitely worse than your telescopes, the ones on our roof, but it's still, I think, a fun time. And so please do come down if you ever have the opportunity. But anyway, my biography is not the one that you signed up to listen about. What we're going to talk about today is the Milky Way. And I wanted to start by just presenting some of the different ways that we observe and conceptualize the Milky Way. The first one that I think most of you would be very familiar with is what you see when you look up in the night sky. And this is roughly what you see, especially if you take a photograph with a camera. And I've written you here, not me, because the truth is I've actually never been to a really, truly dark sky yet. And so it's really high on my bucket list to eventually do that. But as I'm sure you've seen at your meetings, you see this beautiful band of the Milky Way. And if you have, a 6-inch telescope like the one that my granddad used to have, you'll be able to see about 20 million stars, the Milky Way, that are bright enough. You'd have to really move your telescope around a lot to see all of them. But there's about 20 million stars that would be accessible to your telescope if you had something like a 6-inch. Moving on from what we can see when we just look at the night sky, there's the data sets that we actually use as astronomers. And here's an example of one of those data sets. This is from a space observatory called the GAIA Space Telescope. And what I want you to appreciate is that this is not an image of the night sky. This is actually a map of star count. And so it's taking where Gaia has observed all the stars that it's seen. In total, it's observed about 1 billion independent stars, which is crazy. It goes down to a magnitude of 21, this observatory, and it can individually resolve about 1 billion stars. And so what you see here is a map on the sky with the plane of our galaxy aligned in the center of where all the stars are. And so all this dark structure you see is where dust is preventing us from seeing more stars. And in the south, you can actually also see our two closest, largest neighboring dwarf galaxies, the Large and Small Magellanic Cloud, which I hope some of you have been lucky enough to see from the southern hemisphere. I also still haven't done that, but it's on my bucket list. And so this is the kind of data set that we use as astronomers, where we go from the 20 million stars to about 1 billion stars in these data sets, where we can get individual information for on the order of billions of stars from this type of observatory, but also other surveys that we've used. And what astronomers then do is they take this data that we have, and we then infer what the rest of the galaxy looks like. And that's how we form pictures like these. This one is, of course, an artist's impression of what we think the Milky Way looks like, given the stars that we can see. Of course, we don't see all the stars. There's stars that are hidden behind dust. There's stars that are simply too far away or too faint. But we use what we can see and then fill in the gaps. And that's how we come up with this number. So we think there's about 200 billion stars in the Milky Way. And that number is, of course, very uncertain because we don't see all of them. But that's kind of where this picture emerges of our Milky Way as a galaxy with about 200 billion stars, maybe roughly that many planets as well. And one of the key features that it has is that it looks like this beautiful disk. And we can immediately see that when we even look up at the night sky on a dark night. And so astronomers have spent a lot of time in the past decades really piecing apart the Milky Way that we can see and breaking it up into the different structures that are visible today. And you see on the right here a breakup of many of those, where, like I said, mainly there's the disk, there's also this bulge, this spherical component in the center of the galaxy, and then this beautiful wispy halo of stars. It makes up, a very small portion of the galaxy, but there are stars that don't seem to belong to the disk of the galaxy, but instead are kind of whizzing around further away. And so this is really our best picture, of course, a cartoon, of what our galaxy looks like. But the main thing I want to get into today is not what the galaxy looks like, but rather how it came to be this way and why it looks like this. What are the actual physical processes? What are the laws of nature? And what is the story that had to occur for the galaxy to look the way it does? And so the story I want to tell today is split up into 3 chapters. They're of uneven length. The first chapter, and the longest one, because it's the one I found most interesting when I first learned about this, is the birth of the galaxy. Why is the Milky Way where it is today? What did it look like when it first came into existence? And why did it first come into existence? That's the kind of questions I'd like to answer to start with. Why do galaxies form? And in particular, what's our best picture for why and where the Milky Way formed? Following that, I'm going to talk to you a little bit about the growth of the Milky Way from that stage of infancy to more of what we see today, where it's this beautiful, ordered disk galaxy with these spiral arms and features. And then finally, I want to end by just sharing some exciting pieces of information about the fact that our galaxy eats other galaxies on a very regular basis. And that is, in fact, a large part of the work that I do and that some of my colleagues do. And so I wanted to close by just sharing some of our perspectives on that and the fact that our Milky Way is not just growing in isolation, but that it's continuously in this process of eating and consuming other galaxies around us. And so, throughout the course of this talk, I'm going to go into some details of research that astronomers are doing. I want you to really, to take away from this talk, is not the specific details of the physics or anything like that, but it's more of the overall story time. I'd really love it if you would all kind of leave this talk with this bird's eye view of the fact that our galaxy has this story, this biography, and that there's a lot of personality almost that you can ascribe to it. That's what I want to convey through the talk. And so also please feel free to, interrupt me with questions if you have any. I think with the format, with all of you in that room, it might make more sense for questions at the end. But if anyone has a really pressing question, you can feel free to interrupt me.
Vedant,
Uh-huh.
could you talk a little more slowly for us, please?
Sure, perfect. I will slow it down.
Thank you.
Great. So yeah, let's go into the first chapter, the birth of the galaxy, and how our galaxy came to be where it did through what is essentially dark matter. And so I'll start off with maybe the only piece of physics that I want to share in this talk, which is this idea of dark matter. For decades, astronomers have suspected and known and measured that there's some extra material out there in the universe holding together galaxies over and above what we can see. And what I show on the right here is a plot from a scientific paper that's been kind of made more artistic, demonstrating the first way that we came to realize that this dark matter must exist. And this was work done by astronomers like Vera Rubin early in the last century. And what this observation does is it looks at disk galaxies like the Andromeda galaxy and other galaxies near the Milky Way. And all they did was measure how quickly are the stars or gas orbiting around that galaxy. And if all the gravity in that galaxy was coming from what we can see, then there's this prediction for how those stars should rotate. And that's this dashed line that you see over here. Eventually, the matter kind of runs out. And so you should see these declining velocities as you go further and further away from the galaxy. But that's not what they saw. In fact, in every galaxy that they looked at, they instead see the yellow and blue points that you see over here, where the stars continue moving fast, even when you go much further away from the visible extent of the galaxy. And so the natural conclusion here is that there's some extra stuff, there's some extra matter that we can't see. It's not emitting any light. It doesn't seem to be interacting in any meaningful way with the rest of the galaxy, except through gravity. It's exerting this gravity and it's holding these stars together and supporting their orbits such that they can continue moving fast even at these large distances. So that's really how dark matter in the concept of galaxies came to be. And that's where our understanding has now emerged, that we suspect that essentially all the galaxies that we see reside in these larger structures of dark matter, these so-called halos of dark matter. And in fact, there's lots of other observations that astronomers have made that also support the existence of dark matter. But this is the observation that is, I think, most relevant in the context of galaxies. And so I'll show my first fun movie of the evening, which is, now that we have this idea that dark matter is this thing, maybe it's a particle that really doesn't do much except exert gravity, we can then run very detailed computer simulations where we start the universe soon after the Big Bang and then see how does the dark matter behave after that. And so this is one of those simulations run by a group in Germany on one of the world's largest supercomputers. And you can see how you start with this diffuse field of dark matter soon after the Big Bang. Over time, it starts to condense and collapse. And that's because just due to random chance, due to random fluctuations, certain regions have more dark matter than others. They're a little bit more dense. And due to gravity, they then pull the dark matter around them. And those dense regions get even denser, and so on and so forth, until these beautiful structures emerge, this so-called cosmic web that you might have read about. And keep in mind that the only physics happening here is gravity. This is this emergent beauty that emerges just by dark matter falling into itself through gravity. And eventually you see here in the center, there's this particular region that initially perhaps was a little bit more dense, that's now really having this sense of self, and it's forming what we would call a halo of dark matter, this circular distribution of really concentrated dark matter that through gravity attracts even more matter towards it. And in our story of galaxy formation that's emerged over the past few decades, we've come to realize that it's this dark matter that's the really important first protagonist in the formation of galaxies, where it collapses and it forms these structures that can then attract and bring more matter towards them. And so we can run computer simulations like the one I just showed you, where we can also put in all kinds of other physics and allow galaxies themselves to grow by gas falling into the dark matter and creating stars. And what you see here is one of those simulations, where on the left you see the dark matter, and on the right you see the galaxies. And you can see that there's this correspondence. Where there's more dark matter, that's also where there's more galaxies. That's where the galaxies are seated. This all doesn't only exist in simulation land. It turns out that we can also take observations, for example, from the Hubble Space Telescope, of where we think the dark matter is and where we know the galaxies are, and we can then relate them. And again, you can see how there's this correspondence. And here I'm totally skipping over how we actually measure where the dark matter is. If anyone wants to hear more about that, feel free to ask a question after the talk. But the short answer is it's through the lensing of light caused by gravity. So although we cannot see the dark matter, we can see galaxies behind the dark matter, and the dark matter then lenses that light, and we can use that to infer the distribution of dark matter in clusters like this. And so I'm totally skipping over that detail, but that's kind of how this measurement is made. And it's just to convince you that all this doesn't only exist in simulation land, but we see this correspondence in the observed universe as well. And so this really is our picture for what the infant Milky Way looks like. This is this gorgeous artist rendition that I found, where the dark matter coalesces, and in that condenses the early Milky Way through the accretion of gas. And the story time I really want you to take away from this is that it's this really chaotic place to be, because there's no really well-defined sense of center. There's all these different chunks of Milky Way that are condensing and forming stars, and they're all kind of fighting with one another and moving around in this spherical orientation. And so really, this is a Milky Way that looks nothing like the Milky Way that we have today. Not only is it, of course, much, much smaller, but it's also much more chaotic. And it would really look unfamiliar to us if we were to see it. So this is a bit of story time. Can we actually try and figure out what this infant Milky Way looks like for the Milky Way itself? Can we get any handle on this population of stars that were formed in this very early Milky Way today? And it turns out the answer is yes. And this is actually something that I worked on a couple of years ago, so I'm just going to briefly flash it. But it's the idea that we can look at these data sets of stars. This is, again, that same data set with about 1 billion stars in it. And we can search for what we think are the oldest stars in that data set. The way we do this is through chemical composition. We can search for the stars that appear to be the most chemically primitive, formed before all the other stars in the galaxy. And to cut a long story short, what we find is that those most chemically primitive, what we think are the oldest stars in the galaxy, are right in the center of the galaxy. They form this beautiful spherical structure right in the center of the galaxy. And it's really just the tip of the iceberg. Like I said, the rest of the Milky Way is much more massive. But it turns out that some of the stars in that chaotic early phase of the galaxy are still alive today. And in fact, we can identify them and find them. And that, again, I hope really supports for you this picture that what I'm trying to convince you of is what happened, which is that in this early Milky Way, you had this very disordered, very chaotic, no disk, a very violent phase, of which some of the stars we can still see today. So that's one of the ways that astronomers lend credence to our story of how the Milky Way came to be. But of course, the Milky Way is only one galaxy. And it turns out that there's a trick that astronomers can use to even better understand how galaxies actually evolve over time. And this, again, is something I'm sure all of you are very familiar with, which is the idea that distance is essentially a time machine. And so this is simply due to the fact that light does not travel instantaneously. It takes time for light to reach us from wherever it's coming. And so whenever astronomers look at objects that are far away, we're seeing those objects as they were maybe millions of years ago, perhaps even billions of years ago, if we build a very big telescope like the Hubble Space Telescope. And so that's what astronomers have been able to do with, for example, the images that I show at the bottom here, where we take very deep observations of a really tiny patch on the sky. This is, I think, something like a postage stamp if you held it up at arm's length. But you take deep enough observations that you can see galaxies that are 6.1 billion light years away or 10.3 billion light years away. And you can then take those galaxies and you do some sophisticated machinery to try and find the galaxies that are most like the Milky Way, that are at the same level of abundance, the same level of commonality in the universe as the Milky Way is today. And so you use this to trace back Milky Way-like galaxies at different distances, but that are essentially Milky Way-like galaxies at different times, thanks to the astronomer's trick that I told you about. And so this is another way that we can try to get a handle on what the early Milky Way might have looked like, which is not by looking at the Milky Way, but rather by looking at the polar opposite thing, which is the furthest galaxies in the universe. And these start to tell us what galaxies like the Milky Way looked like 10 billion years ago and 11 billion years ago. And what we find, again, supports this picture, that the earlier you look back, the less ordered Milky Way-like galaxies are. They don't have these beautiful disks, but instead they have these chaotic distributions of stars that are more spherical and more messy and more violent. And I will mention that I'm showing you Hubble Space Telescope data here, but many of you have seen beautiful images from the James Webb Space Telescope. And that, James Webb really was designed to push this kind of measurement even further and look back at even earlier phases of the universe. And so in this chapter, I hope I've managed to give you a brief story of why and where galaxies form, predominantly through this beautiful actor of dark matter that sets things off. And I've also tried to tell you about the two tools that astronomers use to understand the early stages of the Milky Way. One is by looking at the oldest stars in the Milky Way itself. And the second is by looking at the oldest galaxies when they were young, by looking at them very, very far away with big space telescopes. And so with that, I'm happy to move on to the second chapter, which is a pretty brief chapter, and it's the chapter about growth. So at the stage of the story where we are, the Milky Way is this very chaotic structure. How does it start to become the galaxy that we see today? Why does it form a disk? Why does it become a disk galaxy? Why can't it just stay in its disordered state till the present day? And the simple answer to this is that disks are very stable. And that is why you, as astronomers, will see disks almost everywhere you look. The stars, the planets in the solar system were initially formed in a protoplanetary disk, a disk of dust and material around the sun that then condensed and formed planets. We see the rings of Saturn, like this beautiful image from the Cassini spacecraft up here, where again, you have these little clumps of ice and material in this very well-ordered flat disk. It turns out that the universe really loves disks, and that's just a phenomenon that emerges from our laws of physics. Disks are a very stable configuration where the particles in the disk are supported by rotation instead of by their random motions. And in terms of why these disks come to be, the way I like to think about it is it's almost like an evolutionary process where whenever you have some distribution of material that's initially random, it usually has, just by random chance, some preferred direction. There's some overall net direction that's preferred in terms of its rotation. And over time, what tends to happen is that that direction in which that very, very rough rotation is happening tends to become amplified. And that's because stars that already move in that direction continue to do so, but stars that move in other directions through interactions by gravity or by friction, in the case of Saturn's rings, either get lost from the system, they get chucked out, or they get pushed and perturbed into orbits that are more like their stars in this kind of rotating system. And so there's this process of natural kind of evolution that drives, that drives particles towards this more disky configuration. And so this really is why eventually you want this disordered system. This disordered system is going to start looking at itself and saying, hey, we're going to want to have a more stable disky scenario. And it turns out that doesn't happen instantaneously, of course. There is initially this disordered state. And that's because, like I alluded to, in the early stages, there's really no well-defined sense of self for the Milky Way. It's this very chaotic situation where the dark matter has condensed. You have gas condensing and forming stars in little clumps. And those clumps whiz around each other and some of them merge together. But there's no real well-defined sense of center. And so it's very hard for this kind of rotational motion to take over. And this is all very recent work. The paper I'm citing here is from 2023. This really was kind of a very active area of research about why disks form in the galactic context. And I will mention that this is by no means a solved problem, but at least it seems, the indication seems to be that eventually this disordered collection of stars and galaxy and dark matter that you have eventually builds up enough matter that it starts to have a well-defined sense of center around which the stars now orbit in a more ordered fashion. And then this process of natural evolution of the stars and their orbits can take place. And the gas that's coming in can start coming in a more orderly fashion. And that's what then leads to the rise of the disk of the Milky Way. And the best way I know to see this is to, again, just look at it with our own eyes. And so this is another computer simulation run by a professor at Caltech. And it's one of my favorite simulations. What you're seeing here is just the stars in one of these full physics, full dark matter simulations, where we start soon after the Big Bang, and then we watch the Milky Way-like galaxy evolve over time. And what you can see here is, again, this very chaotic early phase of the universe, of the Milky Way, where you have this very disordered collection of stars. But you can already kind of start to see that seems to be starting to try and rotate in a given direction, but other stuff keeps happening to it and kind of interrupting it. But eventually, I think about this time in the movie, it really has found its center. It's built up enough matter that it's starting to rotate along a pretty fixed axis. And after that, it's a pretty quick runaway reaction of self-feedback, where the disk is behaving really nicely. That makes the gas that's falling in behave really nicely and also follow that disk. And pretty soon you end up with a beautiful, fully formed, very well-ordered disk. And so this really is the kind of picture that we think that the Milky Way underwent. Of course, it probably wasn't this exact same picture. We can't know. But that is, again, another thing that astronomers work a lot on, is running simulations like this and then trying to figure out what are the different observations that we can make in the Milky Way to inform the simulation and understand which of these beautiful movies best describes our Milky Way. And so what we end up with then is the disk of our Milky Way as we see it. What you see on the right here is another survey of the Milky Way that I really like, that really makes the point, I think, of just how razor thin the Milky Way's disk is. And one of the other things astronomers have found that I'll just mention is actually that you can probably see it from this image already. Most of the stars in the Milky Way disk do follow this razor thin disk, but there's actually this population of fuzzy stars, if you look closely, that are from this extended disk that's a little bit thicker. It's a little bit more disordered. And so just keep that in mind, that when people say the disk of the Milky Way, there really do seem to be these kind of different populations of stars, where most of them are in this very well-ordered disk, but there is this significant population of stars that's kind of more violent and heated. And the main reason I mention this is because it's a very good way to start an argument between astronomers who work in this field. We really don't know why this is the case. There's a lot of stories, there's a long history of people writing papers about this, but really to this day, we don't have a very clear physical picture for why the disk behaves this way. And there's a lot of ongoing work being done to try and pick and choose between those theories and try and figure out why the Milky Way has these different disks. But generically, the processes that I've described in this chapter of the talk are what govern broadly why disks emerge in galaxies like the Milky Way. Once you have that chaotic distribution of stars, if it has a period of time in which it's left alone, in which there isn't other stuff bumping into it, it'll eventually develop the sense of self, and then the gas that flows in will get increasingly more and more ordered, forming this flat disk configuration. I'm going to have a quick sip of tea, and then move us to the third chapter. That, again, I personally think this was the coolest thing that I learned in graduate school, that for some reason nobody told me when I was an undergraduate in any of my astronomy courses, which is the idea that the Milky Way has had a long and storied history of eating other galaxies. And although we might have suspected that, what I'll try and talk to you today is about the fact that not only do we know that that happened, but we can actually work to reconstruct which galaxies the Milky Way has eaten in the past and come up with a story for how the Milky Way has assembled in terms of the other galaxies that it's eaten over time. And so when some of you were watching that earlier animation I showed you with the stars, you might have already noticed that, I was trying to draw your attention to the disk that was emerging, but that entire time there was stuff flying in and merging with the galaxy. And so that's really what we're going to talk about here. And so again, I think the best way to show this is with another computer simulation that's very similar to the one I just showed you, except in the previous simulation, I was showing you stars, all the stars that are born in the Milky Way and stars that are brought in from elsewhere. In this one, what we're going to see is only stars that are born outside the Milky Way. And so none of the stars that are born in the Milky Way, which make up 95, 99% of the stars in the Milky Way today, we're not going to see any of those. We're only going to see stars that were born elsewhere. And so let's start running the movie forward. And the coolest part about this movie for me is that each star is colored differently based on which galaxy it was initially born in. And so you can see as time progresses, you have this beautiful structure that is almost kind of hidden if you're just looking at the entire galaxy, because again, most of the stars are born in the galaxy itself. But if you pull that veil aside, then you see that there's this rich structure of what we call accreted stars that were not born in the Milky Way, but were born in a similar story time that I've just told you in a totally different galaxy, and then fell into the Milky Way afterwards. And what you end up with is this really messy situation at the present day, where you have this very disordered distribution of essentially brown muck, right? It's all the different colors mixed together. You can't really tell which star came from which galaxy. There's some galaxies that really contributed a lot of stars. So in this picture, you can see the yellow one and even the purple one. If you could observe enough stars in those ones, you might actually be able to suspect that, okay, this all belongs to one thing and the other one all belongs to the other thing. So some of them contribute a lot of stars. A lot of them contribute only very few stars. And so they're all just ripped up and mixed up all over this image. And finally, you'll notice that there's little blobs, even at the present day, that are still present in the simulation. And that's the galaxies that the Milky Way has not eaten yet. And what I'll show you is that this is all true. And what astronomers have really worked on over the past decade, but also just in the past 10 years, a lot of progress has been made on this front, is of understanding what this map looked like for the Milky Way and working on actually piecing apart the different colors for stars that we actually observe. where of course we don't know the answer and we don't know where each star came from. And this is all the work of this field called galactic archaeology, which is a name I really like. And it's the work that I initially came to grad school to do. And that's this idea that you can use stars as a fossil record to try and reconstruct where those stars initially came from. And so we treat these stars as relics that contain certain pieces of information. Chiefly, we can use the orbits of those stars, the ways in which they're moving, where they're located on the sky. We can also learn about the chemical composition of stars, because stars in different environments and in different regions tend to have different signatures of chemical elements on their surfaces. And these are measurements that we can make as astronomers. And so, for example, a star born in the Milky Way or a star born in another very tiny galaxy in a different place could have different chemical composition. And astronomers can actually make measurements that can differentiate between those two. And so this field is all about taking these measurements of individual stars and then trying to reconstruct this picture here by splitting stars apart based on where they are, how they move, and what they're made of. And I'll just share, I think, maybe the most significant finding that's come in the last few years. This was actually a finding only in 2018. So I was in my first year of college when this was discovered. And that was this idea that we now really strongly suspect that the Milky Way underwent a very major transformative merger with another galaxy about 10 billion years ago. And so here's a movie that I'll show that gives a schematic of what this merger might have looked like. You can see that there's the smaller dwarf galaxy that collides with the Milky Way that seemed to already have a bit of a disk by then, and then forms this, kind of halo structure of stars around the Milky Way. And so like I showed in one of my first slides, the Milky Way has been known to have this halo of stars, this spherical distribution of stars that are further away from the disk and seem to be more in this kind of random spherical configuration. That's been known for decades. But really the revelation in just 2018 and in the years since then is that the majority of the stars in that halo were deposited onto the Milky Way by this one merging event. We can really piece apart the stars. We can survey the stars in the halo and look at the way they're moving and look at their chemical composition. And the bulk of them appear to belong to this one merged event. Now, of course, this is a very difficult statement to make. It's a very difficult measurement to make. So there are some competing theories. But this really is a consensus that's starting to grow in the astronomical community, which is that the majority of the Milky Way stellar halo seems to have been deposited by this one major merger event about 10 billion years ago. Another key part of this is the fact that since then, so in the past 10 billion years, it really seems like the Milky Way has had it easy, which is another reason that we have this beautiful ordered disk that we have, which is that after this event 10 billion years ago, we seem to have had 10 billion years of reasonably quiet history. We have, of course, been consuming and merging with other galaxies, but they've tended to be on the smaller side. And so they don't really disrupt the Milky Way as much as this merger must have. And so, yeah, really, this is one of, I think, the coolest things that I learned in grad school, which is that we now can really definitively say that we think this merger happened. And now there's a lot of work being done to understand how this merger shaped our galaxy and how different properties of our galaxy can actually be explained by the fact that we think that this merger happened. Now, of course, these mergers aren't only ancient history, and the mergers continue all the way to the present day. So like I said, if any of you have been in the Southern Hemisphere, you would have seen these two beautiful nearby galaxies, the Magellanic Clouds. These have been known to humanity since antiquity. They've been written about in cultures dating back centuries. And the sad story is that we are eventually going to eat them too. And so people have run models of what's going to happen to the Magellanic Clouds in the near future. And the prediction is that over the next billion years or so, the Magellanic Clouds are going to slowly spiral in, and the Milky Way is going to consume them as well. And so not only the Magellanic Clouds, but also now astronomers have identified dozens of other small galaxies that surround it. And the expectation is that just like the past galaxies that the Milky Way has eaten, eventually it'll eat those too. And so that's kind of a rough idea of what the Milky Way's diet is going to look like. We can actually see these intact galaxies around us, and we know that in the fullness of time, we will consume them as well. And so on the topic of mergers, and finally looking just a little bit ahead into the future, there's this final merger that many people love talking about. And so I wanted to show this really beautiful image that the folks at the Space Telescope Science Institute put together. And that is the fact that the Milky Way seems to be moving towards our largest neighbor, the Andromeda galaxy. So in about 4 billion years, 4.5 billion years, we have nothing to worry about, but still quite a long time away. The expectation is that the Milky Way and Andromeda will start to merge and start to collide. And these galaxies are so massive and these scales are so large that it would actually take another 1 or 2 billion years before that merging process is complete. That's how slow this dance is. The other interesting thing about this is a question I get asked very often, is should we be worried about bumping into another star when this happens? But of course, you all know stars are incredibly far away and there's a lot of empty space between them. And so people have run models and they've calculated that the highest probability is that there will be 0 direct stellar collisions when the Milky Way collides with Andromeda. That being said, the Milky Way stars will, of course, exert a lot of gravity on Andromeda stars. And so the expectation is that these beautifully ordered disks that the Milky Way has and then Andromeda has, those will finally get destroyed. After the 10 billion years of quiet history that we've had, about 4 billion years in the future, the expectation is that we will merge with Andromeda, and finally that sense of order will be broken a little bit, and will probably form what's called an elliptical galaxy, a more spheroidal distribution of stars. And so this is our best picture right now of what we think the future might look like. Again, there's a lot of ongoing work here about whether we'll actually collide with Andromeda and what that might look like. But this is our most plausible story for, on a longer time scale, where the Milky Way is headed. And so I wanted to conclude by laying out the timeline of everything that I've discussed today. And again, I think I've conveyed a lot of information, but I want to leave you with the overall story time of what the story of our Milky Way seems to be. And I'll note that the title of my talk is not The Biography of the Milky Way, it's A Biography of the Milky Way. There's a lot more work to be done on this, of course. But a plausible story seems to be that the Milky Way was born in this kind of proto-galactic phase, in the first few million years after the Big Bang, perhaps, based on the observations that we're now seeing with telescopes like James Webb, where we see stars emerging and galaxies emerging very soon after the Big Bang. This is followed by the spin-up of the Milky Way's disk, which again seems to have been a pretty early event in the first 1 or 2 billion years after the Big Bang. The GYR here is the astronomer's term for billions of years, it's gigayears. The next event, of course, of note is this major merger that seems to have happened about 3 billion years after the Big Bang, roughly 10 billion years ago. And now there's really kind of more rock solid evidence that this appeared to have happened. And this appears to be the last time that the Milky Way as a whole has had to worry about big mergers messing it up. Subsequently, it's eaten other smaller galaxies, but this was the last transformative one. We then skipped forward about 10 billion years of quiescent history to the present day, where over time the Milky Way's disk has grown and the structure that we see today has emerged. I'm obviously skipping over a lot of details there, and there's a whole other talk about what that evolution has looked like. And then finally, just pure speculation, where maybe in the next 4 billion years, we'll have this merger with Andromeda and end up with a sky that looks very, very different. And so that's a biography of the Milky Way. It's really been a pleasure to talk to you about it. I think we have plenty of time for questions, but I really would like to thank you for your time.
Thank you.
Bill, would you like to ask a question?
Sure, thank you. Regarding the merger, can you figure out which globular clusters belong to which galaxy?
Oh yes, and that's actually one of the pieces of evidence that was most convincing when these discoveries started to be made in 2018. So initially, the merger was caught due to just the stars. There was a population of stars that appeared to have orbits and compositions that all matched each other to the extent that they seem to have come from the same initial galaxy. But then people did work matching those stars with globular clusters. And indeed, there's an entire population of globular clusters that we've identified that appear to have orbits that kind of look like stars that belong to this structure. And they actually have structures in their chemical compositions as well that appear to link them to this merger. And so, yes, there's globular clusters that we think are definitively associated with this merger, and also actually with some of the smaller mergers that I mentioned. It's a big part of galactic archaeology to match not only stars to the different mergers that we think the Milky Way underwent, but also match the globular clusters. And they actually teach us a lot, because globular clusters teach us a lot about not only chemical composition, but also ages. It's very difficult to know the age of any individual star, but it's much easier to get the age of an entire globular cluster. And so that's just one of the ways in which we use globular clusters a lot for our work.
Thank you. Mario?
Two questions, if I may. One, since there is a tendency to flatten out as a disk, why do elliptical galaxies exist? Okay. And second question is, if the Milky Way was built up by a merger of multiple smaller galaxies, why do we see more cores of these galaxies, which I would expect to persist, such as Omega Centauri?
Sure. So I'll answer the first question first, which is, again, this has been a very active area of research for a long time. One of the suspicions seems to be that the precondition for this ordered disk forming and it being stable is that it's left to its own devices. And so one of the ways that can be disturbed is if you have these ongoing mergers that never let you form the disk in the first place, or as will be the case with Milky Way in the future, where you do form the disk, but then you merge and you form this elliptical configuration. And so that's one of the main stories, is that if you have kind of a more chaotic merger history than our Milky Way has had, and you're not privileged with this period of quiescence, then eventually you'll hit something big enough that you then form this spheroidal elliptical distribution of stars. And the thing to keep in mind is that once you have a population of stars that's elliptical, then it is pretty hard to make that flatten down and form a disk. It really is something that should happen when the stars are forming in the first place. It's much easier for the gas that eventually forms those stars to form that disk configuration. The stars left to their own devices will kind of stay the way they are for a very long time. And so it's a question of how peaceful the galaxy is at the time when it's forming most of its stars. We think that seems to be the thing that mediates it. And then, of course, the other way is you form a disk and then you hit something else and then they get destroyed. For your second question, could you actually just repeat the second part of it? I'm not sure I fully grasped it.
If our Milky Way was built up by smaller galaxies, which I think I agree with you, I think that is correct. It's felt that Omega Centauri is the core of one of these smaller galaxies. Why do we see more Omega Centauris?
Yeah, that's a great question. I think so. The status of Omega Centauri is still a little bit uncertain, but indeed, as you said, people think it doesn't really seem to be a normal globular cluster. It could be the core of one of these mergers. The reason we don't see more of them, I think, is if the galaxy that merges itself smaller, then its core will be much more susceptible to getting ripped up. And B, if the merger happened, earlier back in time, then again, given more time, the Milky Way will rip apart those cores. So these cores aren't, there's no expectation that these cores will live forever. The moment a galaxy falls into the Milky Way starts stripping it, not only of its stars, but also of its dark matter. And so although some cores persist, like Omega Cen, like the Sagittarius dwarf galaxy that's currently merging with the Milky Way, that still has a core that we can see. The expectation is, and especially when we run these simulations, we can see that most of the cores over time dissolve. And so it's just a question of which ones you catch in the moment and which ones you don't.
Okay, thank you. I'm going to sneak in a question here. Vedant, could you explain the origin and the seeming stability of spiral arms?
That's a tough one. So that's another very, it's very common in astronomical conferences that someone will stand up and say, I don't believe in the spiral arms. So really, I will say there's some debate in the astronomical community to what extent the spiral arms even exist in the Milky Way. We know they exist in gas. And in fact, it's from the roof of the building I work in here in Cambridge, where some of those spiral arms were discovered for the first time. When you make observations in the radio, you don't care about light pollution. So they actually made those from Cambridge. So the first thing I'll say is that is the existence of spiral arms in the stars is a little bit debated. One of the main explanations now that people think is what happened is that the spiral arms are kind of over densities in the orbits of stars. And so, when people first started trying to study spiral galaxies, they realized that they couldn't be these long-lived structures where the stars themselves are living in the same spiral arm, because very quickly, the stars in the center orbit faster than the stars that are further away, and so it would kind of wind itself up, right? The spiral arms would wind themselves up and twist themselves up. And so what seems to be happening is that there's these density waves, these corrugations in the galaxy, where stars kind of move into a spiral arm, slow down for a while, and then move out. That's the density wave theory of spiral arms, that if you were to ask people who work on orbits and dynamics, they'd give you that explanation for spiral arms. But really, like, this is a very, very active area of research, and is another fantastic way to start a fight with an astronomer.
Any other questions? Yes.
I have,
Yeah. Oh, is he there?
Alan, is that you? Go ahead.
yes, I thought I heard somebody else start before me.
No, you go ahead, Alan, and we'll get to you in a minute.
I'm finding this absolutely fascinating, but I'm a layperson, unlike half the people in the room, and I don't quite understand what you just talked about. Some people not believing in spiral arms. You mean not believing our Milky Way has spiral arms? Because obviously millions of other galaxies have spiral arms. I didn't quite understand the theory behind all that. Could you take another moment just to focus on that?
Definitely, yeah, no, that's definitely very important. So what I was alluding to there was the fact that of course, many other galaxies have spiral arms, but we also know of other disk galaxies that don't have spiral arms. And so that's been an ongoing debate, is not only does the Milky Way have spiral arms or not, but also how many, right? People have claimed that there's some spiral arms that then get disproven. And so, the image we see of the Milky Way from the center, you can see this here. You can imagine how hard it is, right, to individually piece apart spiral arms, because we're not blessed with this face-on view of the Milky Way. We have to infer all of that from the plane of the galaxy. So one of the ways there's a debate is how many spiral arms there are and where they are, but also the fact that it's been easier to find those arms in gas than it is to find them in stars. And so that's been the other debate, which is to what extent the spiral arms exist in the stars of the galaxy, or is it just the gas that has these arms and the stars are kind of more uniform? So people are always looking for different ways to search for the spiral arms. And as we get more, deep data that covers more of the Milky Way, that isn't just confined to the bubble around the sun, that'll help us answer these questions.
Thank you. I might have read that in one of Bill Walker's books a while ago, but I don't think it connected. I didn't know this was a controversy. Thanks.
Mm-hmm.
All right, we have at least one more question here, a couple, and then we'll get to the people online. You want to go ahead?
Yeah, my question is, I noticed you never mentioned black holes.
Oh, yeah.
What role would that have?
Yeah, you all are finding all of the hot topics and controversies in astronomy. And so indeed, there's a long history and tradition of understanding how black holes interact with their galaxies. And this is driven, of course, by the fact that we now know and believe that not only does the Milky Way have a supermassive black hole at its center, but that this seems to be generic to many galaxies that are of similar size to the Milky Way. They all seem to have black holes at the centers. So this is, again, a very ongoing topic of research. One of the ways people think that black holes interact with this whole picture is that although they make up a very small amount of mass of the galaxy, one misconception that I overcame when I first came to grad school was I used to think that the galaxy orbits around the black hole. But it turns out that's not the case at all. The galaxy doesn't care about the black hole much. The galaxy is orbiting around the other stuff in the galaxy, and the black hole just happens to, through gravitational interaction, sink to the center of the galaxy. That being said, black holes can become very energetic objects. And so although the Milky Way's black hole is relatively well behaved right now, and it's really hard to observe it, as evidenced by, I'm sure many of you have seen that beautiful orange donut picture of the Milky Way's black hole that was done by people I work with at the CFA. It's really hard to observe it because it's so quiet, it's so quiescent. But in other galaxies, we've observed that if you chuck enough material at a black hole, they can become really angry. And because again, they're these supermassive general relativistic objects, they can convert matter into energy very efficiently, we think, and then really start interacting with the galaxy around them by blowing gas around, by creating more stars because they're blowing the gas around, but also people think that black holes can kill galaxies. If you chuck enough gas at a black hole, it could react and erupt and burp so violently that it blows all the gas out of the galaxy, effectively killing it or quenching it is the term. And so there is this long history of people understanding how black holes interact with the Milky Way. I just didn't have time to cover it today, but it's definitely a very important topic.
Thank you, thank you. You all set?
Same question.
Oh, okay.
So there's theories about how possibly the universe as a whole is older than we think, of the 13 billion years. How does that interact with the timeline of the Milky Way?
Yeah, so I think so. Maybe is there any particular observations you had in mind for that theory? I think one of the main ones that I often see is people find individual stars that they think are older than the age of the universe that we think that are older than we think the universe is, and there I think really the measurement is very uncertain. So there's measurements that we can make to infer the age of the universe. Most of these come from cosmological measurements. Those are pretty, we think, solid. But when it comes to getting the ages of individual stars, which again is just the example that I've seen the most of, that in of itself is very uncertain. It depends a lot on the models we make of what stars are like. And in my opinion, those models are much more uncertain at this time. And so, at least for me, those observations don't make me think that the age of the universe is wrong, but more that our models with stars need to be improved a little bit. Was there any other observation you had in mind? That's at least the one that comes to my mind.
Well, I've just seen a lot of talk that now with the new James Webb data, the universe might be a little older than the 13 billion years. And since the timeline seems to be based off of when the Big Bang was, that obviously would change things if our universe is older.
Sure. So I'm not familiar with that research. I'll definitely look it up after this talk. My main takeaway from the James Webb data has been, if the universe is as old as we think it is, then it seems that the universe is better at making galaxies than we would have initially thought. And I think one solution is that the universe is older than it actually is. And again, maybe there's some other observations that I'm unfamiliar with that make that point. But there's another flip side of that, which is that if the universe is as old as we think it is, then maybe it's just better at making galaxies, because what James Webb is finding is these really kind of well-built, much more massive, they'll end up being much more massive than the Milky Way. So they're not kind of the Milky Way type galaxies I showed you today, but it really is finding, beautifully well-assembled galaxies and beautifully well-assembled black holes much earlier than we might have expected. And so I think, at least to my level of familiarity, that's been the tension with JWST. But maybe the universe is just better at making galaxies than we think. Everything I showed you, all the beautiful movies, have some physics put in them by people. And all of that is kind of subject to change. And that's why we build observatories like James Webb.
Thank you.
All right, anybody else in the room?
I have one question.
Yes.
So this question, after what you said, it sounds like everything wants to flatten out and form a disk type of thing. Well, why isn't the universe flattening out too? I just wanted to throw that at you.
Yeah, no, that's a really, really good question. I think the main reason is it's not something that just happens on its own. It's something that happens when there is when there's an interaction between the particles in the system. And so in the rings of Saturn case, there's collisions and friction. In gas, there's also this collision and friction. In systems of stars, there's gravity. When it comes to the universe, eventually you reach a scale where, although of course everything is exerting gravity on everything, the scale on which the Milky Way and Andromeda are interacting, for example, is so long, right? It's billions of years that that's really not enough time for these processes to take place. So yes, I definitely skipped over many details there. A precursor to that happening is that there's some kind of interaction happening such that many small interactions can build up into that emergent phenomenon. And in order for that to happen, the time scale for those individual interactions has to be small enough that many of those interactions can happen. And when you come to the scale of the universe, those interactions that aren't happening essentially. So eventually you reach a size where those processes aren't relevant.
Take that. All right, thank you. Listen, before we get to the people online, you got a question? Okay. Could you stop your share so we can see the people we're talking with?
Sure.
Thank you.
There we go. Sorry, I have to find the button. There we go.
All right, having said that, are there any questions online? Gee, we went to all this trouble.
It was absolutely fascinating. I loved it. Thank you so much.
Thank you.
All right, I guess we're good. Thank you so much, Vedant. It's really exciting.
Thank you, everybody.
Thank you. It was such a pleasure
Back
to talk
again.
with you. Thanks a lot for the opportunity.
Thank you.
I'll be in touch about your free commemorative t-shirt.
Sounds perfect. Looking
All
forward to
right.
it.